Okay, so in this video, we are going to look at the nomenclature that relates to nonmetals. Now, I'm going to show you in this video, and as all my nomenclatures, I have always covered this, and also in the bonding, where the students get confused. And a lot of it now, naming is obviously, it relates to the bonding also. So let's cover this now. Yes, the formation of charges is when the electrons are transferred, but when the electrons are shared, at that time, there is just basically not leaving the electron cloud, but there's an overlap of the electron clouds where the electrons that are being shared are found. And the whole purpose of sharing is to achieve the octet. But at the same time, if not the octet, but to get a noble gas configuration that is stable, or in other words, somehow they also want to have the fully filled orbitals, right, which are more stable. So the whole purpose is stability. So here I'm going to show you. Look at the nonmetals. The group 1A, we have hydrogen. Okay, hydrogen has one valence electron. So yes, it is going to form one bond. Even when it is sharing the electrons, then even in that case, it can only form one bond. It cannot, when it gives away one electron, yes, that it forms a +1 charge. But when it's sharing, it does not form the +1 charge, but it can still, like in sharing, there's no charge formation. Okay, group 3A, there is boron. Boron is also, there are elements that go through the process of hybridization. Now that is beyond the course, the introductory course, that's only covered in the higher level courses. But for now, just you should know just that hybridization is a process that exists. Okay, now that exists in bond formation. So here we have group 3A, boron. It will only form 3 bonds. Now remember that aluminum gave away the three electrons. That is also in group 3A. But boron doesn't form the ionic charge as far as I know. So boron will go through the process of hybridization in which it forms 3 bonds by sharing, not by the transfer of electrons. Okay, so here we have boron plus 3. There are 3 valence electrons, so 3 bonds. Carbon and silicon, both of them belong to group 4A, so they will form 4 bonds. Okay, so up till now, hydrogen is not following the octet, and boron is also not following the octet. Okay, octet is 8 electrons, so they are defying the octet. But carbon and silicon, they follow the octet rule. They have 4 electrons in the valence shells, so they only need 4. So even by sharing, they are able to achieve the octet. Now come group 5A. In group 5A, we have nitrogen and phosphorus. Okay, now nitrogen and phosphorus, what's the deal with that? Nitrogen, okay, has 5 valence electrons. Phosphorus also has 5 valence electrons. Nitrogen can make charged also species, or nitrogen can also share. So, both the ways, it only needs 3 more electrons. So it can either, gain and form a negative charge, or it can just form 3 bonds by sharing. And by, share by 5 electrons and by sharing 3 electrons. So that's one thing. Phosphorus, group 5A, 5 valence electrons. Okay, it will make 3 bonds, right? To achieve the octet, it has somewhere those 3 electrons have to be either attained or they have to be shared. But phosphorus also has the capability to make 5 bonds. Okay, these 5 bonds that the phosphorus has, these come through the presence of d orbitals. So phosphorus has the capacity to make 5 bonds. So keep that in mind. Phosphorus has the capacity to make 5 bonds, and phosphorus will make 3 bonds also. In chemistry, a lot of it is just the, what's happening here? Okay, a lot of it in chemistry is the environment, the chemical environment, the experiment, but at the same time also, what are they reacting with? So if phosphorus connects with a less electronegative atom, such as hydrogen, it will form 3 bonds. But if phosphorus combines with a more electronegative atom, such as oxygen, then it expands its capability to accommodate the needs of oxygen. So it can make more than 3 types of bonds. So that's going to be like it can make 5 bonds. Okay. So when less electronegative atom, like hydrogen, 3 bonds, but more electronegative oxygen, like oxygen, it can make 5 bonds. Phosphorus can also combine with chlorine and can make 5 bonds. Okay. Phosphorus can make 3 bonds also. That's a normal thing. It's a reaction condition. But if you make the reaction condition a little bit more vigorous, phosphorus expands its capability and it can combine even in the case of chlorine, even in the case of chlorine, it can make 5 bonds. Okay. Now let's look at the group 6A. Now group 6A oxygen. Okay, it's in the group 2, the second period, right? So it only has 2 energy levels. So it will only make, it has 6 valence electrons. It needs only 2 more to, to satisfy the octet. So even in the shared state, it only needs 2 electrons, even in sharing. So oxygen will only needs 2 more electrons, and it can share those 2 electrons from another element, and then it can make, it can have its octet. However, look at sulfur. Sulfur has 6 valence electrons, and yes, sulfur can make 2 bonds just like oxygen. 6 valence electrons, 2 more electrons need to be brought in. So that's the story. But sulfur has the presence of d orbitals also in its third energy level, right? And as a result, sulfur expands its capabilities. So sulfur can make 4 bonds and sulfur can make 6 bonds. So this is why you will see sulfur, when it combines with hydrogen, a less electronegative atom, it makes only 2 bonds. But when sulfur combines with a more electronegative atom, such as oxygen, it can make sulfate, it can make sulfite, it can make sulfur trioxide, it can make sulfur dioxide. You see that? The more electronegative atom, then the sulfur gets more like, very, let's say, hospitable, and it accommodates the needs of oxygen, and it's able to make more bonds. Okay. Now look at group 7. Now by default, group 7, all of them have 7 valence electrons, right? So it should be 7, not 1. Sorry about that. Let me see if I can fix it here. 7. It should be 7. This should be 7 electrons. Okay. 7 valence electrons. And so they only need 1 more electron, and they can make, by the transfer, if they are gaining electrons, like completely transfer of electrons, then it will be charged fluoride, chloride, bromide, iodide, negatively charged species. And it's just going to be 1 bond, or they can form bonds by sharing of just 1 electron they can get from some other atom, and then they can share it, and that sharing happens in a region of overlap. Okay, so that's 1 electron. Okay, 1 electron sharing means 1 bond. That happens when fluorine, chlorine, bromine, iodine combine with a less electronegative atom such as hydrogen. However, when chlorine, bromine, and iodine, these guys, when they combine with a more electronegative atom such as oxygen, then they are capable of making 3, 5, and 7 bonds. Okay, so 3, 5, and 7 bonds is an expanded state. Okay, next comes the group 8A. Now here also, we know that 8A does not make bonds at all, right? We have helium, 2 electrons, no bond. We have neon, argon, krypton, xenon, radon, 8 electrons, again, no bonds, okay? So these guys will not make any bonds because their octets are satisfied. However, remember, it's always reaction conditions. When xenon combines with a more electronegative element, such as fluorine, or with oxygen, then it can make 2, 4, and 6 bonds. Okay, so this thing is very, very important. You are aware of it, because a lot of students, once you start making the Lewis structures, therefore this information I have not seen in the books, and it gets very confusing then. Okay, so just keep this in mind, that hydrogen, boron will not follow the octet. Phosphorus can defy the octet. Sulfur can defy the octet. It will follow the octet, but it can defy the octet. Then comes fluorine, chlorine, bromine, iodine. These guys can follow the octet, but chlorine, bromine, and iodine can defy the octet. And xenon can also defy the octet. It can make 2, 4, and 6 bonds. Okay. Now, this is a general story with the nonmetals. Now, when we name the nonmetals, now look at the naming of the nonmetals. Here, the naming of the nonmetal is very simple. The terminology di, tri, tetra, it applies to the nonmetals. So 1 means mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Okay, so we are going to use these terms. So when we have carbon with 1 oxygen versus carbon with 2 oxygen, with 1 oxygen, it's carbon monoxide. With 2 oxygen, it's carbon dioxide. When nitrogen combines with 2 oxygen, it's nitrogen dioxide. With 3 oxygens, it's nitrogen trioxide. Now, on the other hand, P2O5. So here we are going to call it diphosphorus pentaoxide. Okay, so that's the name of these nonmetals. Okay, now here I'm going to cover the acids also. So keep this in mind that the acids, the monoprotic acids, which contain only 1 hydrogen, will have hydrogen with fluorine attached, and the aqueous means in the water medium. So it becomes hydrofluoric acid. But if it was in a gaseous state, it would have been hydrogen fluoride. Okay, next is with chlorine, it's hydrochloric acid, bromine, hydrobromic acid, iodine, hydroiodic acid. Okay, diprotic acids. Now, you still have to memorize all the polyatomic ions. So, but here comes diprotic. Diprotic is 2 protons. So 2 hydrogens. So if the only thing you have to remember is what is the polyatomic ion? A lower oxidation state will end in us, like sulfurous. When H2SO3, SO3 is a lower oxidation state. SO4 is a higher oxidation state. SO3 is the sulfite ion. SO4 is sulfate ion. Sulfite, the name with H2SO3, that name becomes sulfurous acid, and H2SO4 is sulfuric acid. So us and ic. Us, lower oxidation state, ic, higher oxidation state. Same story applies to the triprotic acid. Triprotic acids are 3 hydrogens. Okay, so 3 hydrogens. Once again, lower oxidation state us, higher oxidation state ic. That is why H3PO4 is phosphoric and H3PO3 is phosphorus, us. Okay, similarly, we have the chloric and the chlorus. Remember, chlorate was discovered first and chlorite was also discovered. So chlorite got the name chlorous acid and chlorate got the name chloric acid. But we discovered the perchlorate and hypochlorite later. So now how do we name them? So hypochlorite, the name is hypochlorous acid. So perchlorate, the name is perchloric acid. Okay, now also there are salt hydrates. Salt hydrates are like the molecules of water that just sit in the ionic, in the crystals. So copper sulfate, so the name is copper sulfate pentahydrate, because 5 water molecules sit in the crystal structure of copper sulfate. Okay, so pentahydrate. Similarly, hexahydrate. So this name, penta, hexa, di, all this, just like you do for the nonmetals. Okay, so now let's look at the nomenclature of these ions. So very simple naming. So we are looking at these problems 6.43, 45, 47, and 49. So here the name is here phosphorus. Remember, 3 bromines, so becomes tribromide. So phosphorus tribromide. And the other is Cl2O. What is that? That is dichlorooxide. Okay, dichlorooxide. Next is N2O3 is dinitrogen trioxide. trioxide. And then P4S3 is tetraphosphorus. Tetraphosphorus trisulfide. Remember, it's just sulfur by itself. Then you have to write the formula of carbon tetrachloride. Carbon is carbon, tetra is 4, and chloride is chlorine. So Cl4. Tetra stands for 4. And chloride is just the chlorine by itself. Okay. Dinitrogen tetraoxide. Dinitrogen is nitrogen 2. Okay. And tetraoxide is O4. But this thing, you know, it should become like this, NO2. But because then it becomes nitrogen dioxide. So don't try to just, whatever the name you have given, just do it for now. Okay. Next is sulfur hexafluoride. So hexa stands for 6. Fluoride stands for F, and sulfur stands for S. So this becomes SH6. Boron trichloride. So boron is B, tri is 3, and chloride is C. So this becomes BCl3. Okay, so this finishes the nomenclature part. Next, we are going to look at the formation of the bonds, how to make the bonds and so forth, the other questions in our next video. All right. Thank you. Bye-bye.